So today we're going to talk about the most important aspect of identifying confidently a structure using non-targeted analysis. And I would say that's fragmentation data. It can really help you get an actual structure, not just the composition of atoms, not just whether it belongs to a certain class of chemicals such as PFAS or not, but the actual structure can be provided by fragmentation in many cases. My name is Jeremy Colmel, and I'm CEO of Innovative Omics and Research Faculty at Yale University, and this is our tutorial on fragmentation. So, as we showed before, accurate mass is not enough. For PFAS, for example, there's over 4,000 formula which could be predicted. And even when using isotopic pattern and accurate mass, while we can get quite high confidence annotations, we still might not be 100% confident in that molecular formula. Not only that, but for the same molecular formula, even if it narrowed it down to one formula, there can be multiple isomers. An isomer is the same molecule in terms of its atom composition, its molecular formula, but the arrangement of atoms are different. So look carefully at the top and the bottom. Sulfonic acid. This is PFAS on the top, and then on the bottom you can see it's branched. The very last two carbons, it's branched instead of linear. And so there's a slight difference, which means that it's probably manufactured via the manufacturing processes that, as of 2025, were still occurring in China, and in some manufacturing processes still in the US, but mostly legacy manufacturing processes in the US, whereas the linear form is the more common new form where they can purely only produce the linear form. And so it tells you something about source, history of the PFAS, but also might have different toxic effects. So knowing these subtle isomer differences might be important. There's certain drugs that have very subtle isomer differences that can mean the difference between saving someone's life or killing them. Here's another example of a structure that can be drawn with those same atoms following our Lewis dot structure principles and work perfectly as well. So that can be a challenge for you guys, is to draw as many structures as you can for PFAS and just see all the possible structures that you can make. And they're quite close to infinite. There's quite a lot of structures. Of course, most of these won't occur and be manufactured by humans, and so we can narrow it down just by knowing what's the most common type. But that's still, we would like to know, especially since we're doing non-target analysis and we don't want to make assumptions, what the real structure is with more information. So for that, we do something called fragmentation. So in fragmentation, what we do is we break apart that molecule, we slam it. You can think of a car slamming into another car, pieces are going to go flying everywhere, or a bullet shooting into a structure and that structure breaking apart. It's the exact same concept. Instead, we're using nitrogen, a triple bonded nitrogen molecule, most common molecule in air, and slamming it into those molecules, or slamming those molecules into the nitrogen, and they shatter at their weakest bonds. And so here you can see, for example, on the top left, one of these structures of types of fragments that are going to occur related to the carbon-fluorine chain. And indeed, if we look at this carbon-fluorine chain, then we would see CF3 minus, C2F5 minus, C3F7 minus, C4F9 minus. You can see it's just breaking apart one part of the chain in another. And because we don't have one molecule, remember in mass spectrometry, we're actually measuring an innumerable amount of molecules, even at part per million or part per billion, part per trillion, there's still an innumerable amount of these molecules. So we're measuring a probability distribution of all those fragments occurring. Other common fragments are for PFAS, and this is by no means a comprehensive list, but giving you some common ones you might come across, are pentafluorosulfide is SF5 minus. sulfonic acid, so like our PFAS and other PFSAs, SO2 minus, SO3 minus, SO2F minus, and SO3F minus are common fragments for those. Carboxylic acids, this is what's called a neutral loss. So instead of describing the fragment in terms of what remains, we describe it in terms of what fell off. So in this case, the carboxylic acid, the class of that molecule, the head group, the CO2, falls off and you're left with the remaining carbon-fluorine chain. Same thing, these are also neutral losses for hydrogen-containing species. So these could be H-substituted species, fluorotelomeres. These are all hydrogen-containing PFAS species. You get these common neutral losses, M-HF, M-H2F2, etc., depending, of course, on the number of hydrogens. You might have ether-containing species, so this is carbon bonded to an oxygen bonded to another carbon. And these are some of the common fragments for those. So you don't have to memorize these. Most software will annotate these fragments for you, such as FloorMatch, but it's just good to know. And especially for these fragments, especially the low mass fragments, there's no other formula that can be predicted for these masses. So if you see a lot of these fragments, especially C2F5, CF3, CF5, some of the SO2F minus, CF3O, those specifically don't have any other mass that can overlap, you're most likely dealing with a PFAS. So even if you can't identify it, this is what we call fragment screening. You might have an MSMS spectrum, which is what we call a spectrum that has fragment data after you smash the molecule apart. And you can just say, hey, this is a PFAS or not a PFAS based on the occurrence of some of these low molecular weight fragments. So this is what an MSMS spectrum would look like. This is actually 4 MSMS spectrum for 4 different chain lengths, carbon-fluorine units, of a carboxylic acid. So you can see the M-CO2 that we discussed for the carboxylic acid. You can also see the chain-related fragments C2F5 and C3F7. You can also see 218, then 249, and if you go to the right to these longer chain species, 218, 249, 268, it would probably be 348, 218, 268, 318, 368, 418, 468. So they're all separated by 50 Daltons. Remember, this was quite a few video tutorials earlier about our homologous series, and that they're separated by 50 Daltons because that's the mass of CF2. These fragments, as you can see, are also separated at intervals of 50 or 100 because those are units of CF2. 100 would be 2 CF2 units. So that makes sense that all of these are part of the fragmentation of this carbon-fluorine chain. Notice also that the distribution, the intensity of fragments is different depending on your species and depending on the fragment. Because, again, that fragment distribution is related to what's the most likely fragment to occur based on the weakest bonds, based on the structure and chemistry when it gets slammed by a nitrogen molecule or slammed into a nitrogen molecule. One more thing I want to note here is that obviously at the beginning of mass spectrometry, everything was done hand annotated. Actually, spectrum would be printed on a piece of paper, and you'd have to write down the mass, you'd have to figure out the mass, figure out what that mass might be. Now with computer-assisted MSMS matching, there's a couple ways we can do that. One is fragment screening, like we mentioned. We can look for fragments and have a list. For example, in our software, we have over 777 fragments that we know what they probably are, and we can screen against them, and then automatically name those fragments. Another thing to do is if we know how a specific molecule fragments, not just what the fragment is, but what a specific molecule, such as these, and you can see that for this class of molecules for PFCAs, they all give similar fragments, as you'd expect. We can create rules. So we can say, hey, I need the intact mass, the accurate mass of the whole thing, maybe even the right isotopic pattern for the whole thing, as we discussed. And I need to see either C2F5 or the loss of carboxylic acid, and C3F7. C3F7 often being the most common fragment that occurs. The closest bond to the terminus that also has the weakest. Because the fluorines pull the electrons for this carbon, actually create a weaker bond when there's not that pull. So for example, for the C2F5. But anyway, so in this case, this is called rule-based annotation. And we and many authors have shown this for different fields as well as lipidomics, other fields where we're also using rule-based annotation. So saying, I need to see this and that fragment and the accurate mass, that if done right, you can get less than 5% false positive rate. So that's very exciting. So that means that the computers themselves can name compounds if you know how those compounds will fragment. And so for fluoromatch particularly, that's what we call a score A, less than 5% false positive. And we have a database with tens of thousands of spectra or rules in this way where you can annotate compounds confidently. Now I skipped this slide over here. This is another way of matching. And this is a very common technique used in mass spectrometry called dot product matching. And just like we had our MS1 isotopic patterns and we had those mirror plots with the theoretical versus the actual, this is the same thing, but instead of the isotopes, it's the fragment spectrum. So the actual thing is on top and the theoretical is on the bottom. And with these mirror plots, we can now get very nice matches. Against experimental spectra or standards. In this case, this is a transformation product. So our body transformed this PFAS into a glucuronic conjugate, and we're able to see how the spectrum match up. Now, as far as data analysis, that might be all you need to know, but there is some other helpful information to just know how this MSMS is acquired, right? So we first have liquid chromatography, which separates out the molecules based on their chain length. Then we can isolate a specific mass at 1 Dalton resolution and measure it. And that gives us our MS1 spectra. And this is all the spectra we were talking about when we were doing isotopic profiling, formula prediction. MS1 being that there's no fragmentation, we're matching the intact molecule in its isotopes. Now, with fragmentation, you're smashing that molecule, in the case of an Orbitrap, into neutral nitrogen molecules, fragmenting them, and again, measuring those masses. And you get a mass spectrum. We'll go a little more detail into instrument configurations and acquiring data in a separate video. So if you're interested in that, I have sparing details here. So now you can see this nice fragmentation pattern, the losses of CO2, and again, the fragments related to the fragmentation of the chain. And here we can see what that spectrum would look like, the data we're looking at. Similarly, with a QTOF experiment, you also can fragment, but in this case, often you add nitrogen at high pressure, and that collides with the molecule rather than the molecule colliding with the nitrogen. And you measure the fragments. Now, we'll again discuss in another video tutorial different ways of acquiring MSMS, acquiring mass spectrometry data. For this tutorial, it's just important to know, in case you haven't seen it before, how the MSMS spectra is acquired. So at any point of time as molecules are coming out of the column, we are measuring them and we want to break them apart. We need to isolate them with the quadrupole. We need to measure the spectrum, and all of this takes time. So we can only select a certain number of ions and fragment them. So the traditional approach is to just select the topmost abundant ions and fragment them. So I'm only mentioning this here, and again, we'll go into more details about even better approaches to cover even more MSMS spectra, to say that as you go through your data, you will miss MS-MS spectra for certain molecules. Certain molecules will not have fragmentation data. So only the topmost abundance at that time will have fragmentation data. Also, because we're isolating at a 1 Dalton window, we may have mixed spectra, and we'll talk about that. Mixed spectra, where two different molecules, either isomers, right, they have the same mass as long as they're coming out at the same time as well. So if they're not very different in polarity or size, and they have the same mass, or if they have very similar masses within plus or minus 0.5 Daltons or less. We will co-isolate and fragment them simultaneously, because while our measurement happens at plus or minus 0.005 Daltons, the isolation actually happens at plus or minus 0.5 Daltons. And so that's just something to be aware of, that a fragmentation spectrum might belong to more than one molecule, which can confuse the issue. So MS-MS spectra is MS-MS spectra. It's the fragmentation pattern with those relative abundances or probabilities of each of those fragments that we can use to help annotate a molecule. There's a number of ways. We talked about spectral matching, where you do the mirror plots. Also, in the case of fluoromatch, along with all the other evidence for MS-MS, you do the class-based MS-MS. That's the rules we talked about, the less than 5% false positive. We can do fragment screening. That's just looking for a fragment and seeing if it occurs in any of our molecules. And if that fragment occurs, they're likely to be a PFAS, and probably a PFAS with a certain substructure. So if it's C2F5 minus, probably has a carbon fluorine chain. If it is SF5 minus, probably has pentafluorosulfide. If it has SO2F minus, it probably has a sulfonic acid. And then there's also in silico MS-MS, where we can predict MS-MS spectra. So again, fluoromatch covers this as well, based on the fact that we know if it has a certain type of structure, such as sulfonic acid, then it will give sulfonic acid-related fragments, and so we can predict based on structure what the fragmentation should be. Now I want to briefly go over the Fluoromatch visualizer, which will also just help you with other software and platforms if you're not using Fluoromatch, to show you how we would use MS-MS. So in this visualizer platform, I filtered to just the annotated compounds, and so we can select a certain compound. So in this case, you see it has an SO2 NH2 at the end. I can click that, and indeed, based on the structure, if you see the far right, it gives you the type of fragments you would expect. So you do see an NO2S. There is a SO2N, which is the same thing, so just reorder the atoms. You can see a C2F5, so that's related to the carbon fluorine chain, and one of that we said was usually predominant for things that have a carbon fluorine chain. And you can see C5F11, which is the loss of that head group, or just the entire chain. So you can see a lot of evidence that this is a molecule. You can also see C5HF11NO2S. This is the N-H. This is the intact molecule. So just because you have fragmentation data doesn't mean that you break it to smithereens. You still often also see your intact molecule. And often when you're acquiring data, you want that intact molecule. This is just a rule of thumb to be about 10% of your entire spectra, and that's kind of a rule of thumb to optimize your energy, because you can change the energy at which you shatter these molecules. Now, here's our intact. So you can see in the tooltips of Fluoromatch, the mass of charge and the fragment mass of charge are the same, because this is the intact molecule. And then you can kind of scroll through and see, okay, here's C5F11, here is C2F5. Note this one shows a branch for the fragment, but you can't actually tell whether it's a branch or not from the fragmentation usually. And so you don't actually know that information. You can also see that some fragments are way more abundant than others. So this NO2S is sky high, whereas all the other fragments are very low. And that gives us information too. For this molecule of NO2S, or SO2N, would make more sense based on the structure to say it in that way. fragments very easily in most of the molecule fragments to NO2S, we expect that for other members of the series. So if we click on another member of the series, indeed, again, we see this NO2S as the predominant peak. See if we have another member of the series. Here we go. So here's another long one. Again, NO2S is the main peak over here. So that's about it. Again, I told you there's one other thing you want to check for the MS-MS spectra, which is if you look at the isotopic pattern, which is very nice, and this is the MS1 spectra, you want to look around the MS1 spectra and make sure that there was no other peaks that were co-isolated within plus or minus 0.5 daltons, and so that our spectra actually belongs to this molecule, which is true in this case. But, for example, let's look at this example. Here you can see a number of peaks, 1, 2, a couple noisy ones over here that are within a very narrow window. They're very close to the molecule, so that means these were also fragmented, probably giving all of this noisy peaks, not just the molecule of interest. So you just have to be careful because you might see something PFAS related and say, oh, this is definitely PFAS, it has C2F5. But if you have something co-isolated with it that is a PFAS, but the one you're looking at, that mass you're looking at is not a PFAS, you can be confused by that. So always check for co-isolation that may occur. There's one other thing that you can do quite easily within the platform here. Just wanted to let you know that that rule-based spectra we're talking about gives you a score of A. So all of these things, if I wanted to filter by A or A minus, are those that met all the criteria of our MS-MS spectra. So these are very nice MS-MS spectra that we see all these peaks that we were expecting to see. And so these are your confident hits. We'll go a little bit over the scoring in a separate video tutorial, but I just wanted to show you that. Now, there's one other thing you can do with fragmentation, and that's called fragment screening here. So I can click, let's say that we look at all of our data, including maybe even unannotated compounds. So we want to look at completely unknowns. So here's all our data. It's like a mess. We can actually say, I want you to give all of the PFAS that give me C2F5. So here I click C2F5, and then I can change the signal intensity cutoff to just those that give a very high abundance, C2F5, for example, right? And now if I click any of one of these molecules, they're very likely to be a PFAS because they have a C2F5. Some of them may even be unknowns. It looks like a lot of them were already annotated, which is good. It's showing that this is working. So here's one that's not annotated. So I will click it. And you can see here that it has a nice C3F7, a C2F5, and that its MS1 spectra is quite clean. You know, there's a little overlap, but you're really looking for things that are very big because they contribute a lot to the fragments. Since we only have 2 major fragments and we only have 1 major MS1 peak, then that relates to our molecule of interest, and this is likely a PFAS. And so that's how you can use fragment screening. You can also now look at formula prediction and figure out that it was an source fragment M minus CO2 of a C10 PFCA. But we'll look into that later as well. And so with that, we'll close our class on fragmentation and fragmentation data. I hope you learned a lot, and as always, feel free to put questions in the comments, and there's links to more resource in the comments as well.